I would say that, a lot of discussion about certainly where we're going is very important, right, in terms of the long-term view for quantum technology and certainly in quantum computing, right, because there's all these exciting advantages that we know are provable and ones that we want to get to for cryptanalysis, for drug discovery, for boosting machine learning, right? And so you can think about it basically. This timeline is over the next several years that we want to get towards that. The concept of building quantum computers has been around for quite some time, but really the ability to build reliable qubits that can actually be that have enough quality so that you can actually see quantum effects has been a real challenge. A lot of the initial efforts were around highly coherent quantum systems, like atomic system, trapped ions, magnetic resonance, nuclear magnetic resonance were some of the first types of demonstrations of actual qubits and even algorithms around those types of qubits. And superconducting was definitely lagging, and everyone had certainly thoughts about the quantum phenomenon within superconducting qubits, but it took a lot of effort and many years of work to develop the right types of interactions between various circuit elements that one can build using superconducting materials to get to the point of actually building a qubit that would be stable enough and one that could actually be usable and controllable enough to start to do more with and to scale up with. That's really one of the most probably the quintessential challenge of quantum computing is this struggle of building these qubits, which are supposed to be extremely coherent and reliable, and yet anytime you try to control it, you end up adding a pathway for it to what's called decohere or lose its information. And so that delicate balance has been the real challenge for pretty much all experimental quantum computing for the last 20 so years, right? Yeah. And a big part of sort of where we've gotten with superconducting qubits has been a consistent improvement of the underlying materials, the underlying circuit elements, to the point that now we can actually build, superconducting qubits, superconducting processors, quantum processors of up to several hundreds of qubits. One of the most exciting things about the field and the industry is just how rapidly things have moved, but also in a positive way, how fast it's moved has really brought in a lot of very talented people and brought together a lot of different parts of the ecosystem, like we mentioned before, academia, national labs, all kinds of industries that are interested. When I started, I would say that the usual path was, you want to go be a academic professor, right? And when I started at IBM, there was not many people doing industrial research in quantum computing. There's probably like 8 of us on the team. And I'd say that a lot of it that changed was just the field moving together, but also just driving the technology to a point where it started being less of just a physics experiment, but you started being able to bring in all these other disciplines. Like when we actually first put the first system on the cloud in 2016, that actually represented a shift of, wow, I don't need to be a physicist in a lab to turn knobs and to do experiments live. I can actually program on a web interface and use the language of quantum circuits. And so then suddenly you bring in abstractions, and it starts looking a little bit more like a real computer. And since then, with open source and with the development of various different software layers of the stack, we've actually built an entire ecosystem that allows different talented individuals with different backgrounds, computer science, engineering, all kinds of different areas, to have that entry point into quantum.
Okay, so maybe I'll take the first part, which is that, at IBM, we've chosen superconducting qubits. We're putting our money behind superconducting qubits. We have expertise in superconducting qubits. And a big part of that is that when you're looking at how to judge these various platforms, there's a few metrics that you want to look at. There's the scale, right? How large of a system can you reasonably build using the techniques that and the technologies that you have to scale up, right? There's quality, right? So when you want to be able to run a quantum circuit, how accurately can you really get the result back? And then there's speed. Speed, you might not think is as important, but actually is important when a long algorithm that you need to run requires many, many collections of quantum circuits. The total throughput of your problem through your quantum processor is going to be very important. So scale, quality, speed are facets that are really important to look at for any of these quantum systems. And with regards to superconducting qubits, scale, we're able to now push towards levels of nearly 1,000 qubits. With new techniques of modularity that we're going to look at to further scale. Quality, we're at 2 qubit gate fidelities, which are like 99.9, right? 10 to the minus 3 errors. And then speed is at the microsecond scale for getting circuits in and out, which is 1,000 times faster than certain atomic systems. And I think the main thing, though, we'll call it a mature quantum computer, is really the ability to build in reliable quantum error correction.
Yeah.
And that means fault-tolerant quantum error correction. And there's certainly a lot of strategies that have been proposed. At IBM, we recently had a result that talked about something based off of what's called a low-density parity check code. It all comes down to the total overhead of the number of physical qubits you need in order to have encoded logical qubits. We need to bring that down so that we can then, overall, as we scale, start to address some of those problems like the sizes needed to do something like Shor's algorithm. I would say that, a lot of discussion about certainly where we're going, right, is very important, right, in terms of the long-term view for quantum technology and certainly in quantum computing, right, because there's all these exciting advantages that we know are provable and ones that we want to get to for cryptanalysis, for drug discovery, for boosting machine learning, right? There's a lot of that in store down the road. But we need to get there in a way that we're not also just sort of neglecting the near term. Because in the near term, what's really exciting is that we're already also at the scale of systems which, at a few hundred qubits, for certain types of problems, which challenge the most advanced supercomputers, traditional supercomputers that we make today. Now, there's a huge gap between that statement I made, that we're at the point where we're challenging the best supercomputers, to, say, finding an advantage for what you can do with these types of near-term quantum computers. But at least this phase that we're in, which we're calling at IBM quantum utility, is an exciting one to be in because we're at the point where you need to use quantum computers to even be in the game to do certain kinds of mathematical calculations to compare with the best supercomputer HPCs that we have. And so in that front of having this as a tool to advance quantum information science, to advance the best techniques of leveraging quantum circuits to develop, say, better algorithms down the road, is a truly exciting thing for the next few years, and absolutely one of those that needs to be part of any sort of certainly national strategy or business strategy to say, how do I make quantum become part of my overall computational framework, right? Not just HPC and not just AI, but also now I need to add quantum as part of it. And so I think that certainly is a really exciting period to be in. So, so where we are today, we're at several hundreds of qubits. Okay, and so these are systems which, like I mentioned before, are what we're calling this like utility error, where just there are certain types of problems that you look at that are challenging for traditional supercomputers that we can also use, that we would look at on these quantum computers. The business advantage of this is sort of to be seen, and kind of you need to use it to find it type of thing. We have a roadmap that continuously scales us towards hundreds of thousands of qubits over the next decade. So along those paths, there's going to be technological hurdles that we need to overcome. At the same time, there are theoretical challenges to bring in this concept of error correction, to bring down the overhead so that at 100,000 qubits, we're actually able to handle some of these problems at scale that we mentioned earlier about simulating molecules or cryptanalysis, et cetera. And so, you can think about it basically, this timeline is over the next several years that we want to get towards that.